Last time we looked at exponential functions, and what we saw is that when we have an equation of the form y equals b to the x, where b is a number greater than 0 and not equal to 1, then that defines a function. And we also looked at the graphs of these functions. Now, the graphs of these functions have certain common properties, and they have two basic shapes depending on whether the base b is greater or less than 1. If the base b is greater than 1, we get an equation that looks like this. It's increasing, it has a y-asymptote at the point 0, 1, and it also includes the point 1, b. Furthermore, it has a horizontal asymptote at the level y equals 0. And if b is less than 1, then we get a similar sort of shape reflected across the y-axis. And so the graph, if b is less than 1, looks like this. We still have a y-intercept at 0, 1. We still have the point 1, b on the graph, only now because b is less than 1. That lies lower on the graph than the y-intercept. And we still have a horizontal asymptote at of the x-axis. Now, in either of these cases, we can see that the exponential function is 1 to 1. In either of these cases, it passes the horizontal line test. It's either increasing if b is greater than 1 or decreasing if b is less than 1, and therefore this function has an inverse. So this is a 1 to 1 function, so it has an inverse. Now, how would we go about finding the inverse using our previous strategy? So step 1, well, we'd write it in the form y equals b to the x, the way that we have. Step 2 would be to exchange the roles of x and y. And we'd write x equals b to the y. And then step 3 would be to solve for y. And now this is the point where we would run into an issue if all we had to work with was what we've seen so far. We know that these exponential functions, the various exponential functions with their various bases, are invertible. They have inverse functions, but those inverse functions aren't able to be described using the arithmetic combinations of functions that we've already seen. But because these functions, these inverse functions, are so important to us, we are going to use them all the time, and so we're going to give them a name. So at this point, we're going to introduce some new notation known as the logarithm. So we're going to use the logarithm to describe the inverse function to exponentials. So the logarithm is a bit of an unusual word. The etymology is not completely clear. But the notation that we're going to use comes from the three first letters of it, log, and our notation is going to sometimes be called log notation, and we will often use the syllable log as an abbreviation for the word logarithm. So let's go to the definition. And we're going to do it the following way. The logarithm with base b, where b has to follow the same rules as for exponentials, greater than 0, not equal to 1, is defined, or is a function, I should say, defined by, in the following way. Defined by The logarithm with base b of x is equal to y if and only if b to the y equals x. Okay, let's take a look at this. Let's break this up a bit. First of all, you'll notice that this b to the y equals x piece right here is precisely the equation that we reached in step 2 in the previous slide when we were working to find the inverse of the exponential function. This is no accident. The definition of logarithm here will allow us to demonstrate that this logarithm is in fact the inverse function of the exponential function with base b. Over here on the left, the logarithm notation, it's important to note that this whole expression, log with the base b, is all one notation. Just as there are infinitely many different exponential functions, each with its own base, there are infinitely many different logarithm functions, each with its own base. So just like the functions 2 to the x, 3 to the x, 1/4 to the x, etc. are all different exponential functions, they have inverses that will be logarithm with base 2, logarithm with base 3, logarithm with base 1/4 in the same way. So first of all, this log base b notation all goes together. Anytime we have a logarithm, we need to know what base does this logarithm have. The next thing to note is that the logarithm here is a function. It's not a number itself, and so it doesn't ever make sense to say that, oh, the logarithm with base b equals some number. It always has to be logarithm with base b of some argument. So this x here is the input to the logarithm with base b function. Now, for the sake of keeping things tidy, we often don't write the parentheses here, but we can. We can also write log base b of x. This is perfectly correct. And when the argument that goes into the logarithm is more complicated than just a single symbol, we will usually write parentheses around it. So we could look at things like log base b of x, log base 3 of 5, log base 7 of x plus y squared. All of these are expressions that involve this logarithm function. The way to think about the logarithm, there are a couple of different ways of doing it. The most important is to use this definition here. Sometimes we don't use the formal definition of the functions that we work with very often, but in the case of the logarithm, we absolutely do. The point that we're going to take advantage of a lot is that the logarithm, an equation involving logarithms, has an equivalent form involving exponentials and vice versa. One of our most useful tools when working with these logarithms is going to be converting back and forth in between the exponential and logarithmic forms of an equation. So this is the logarithmic form of an equation. This is the exponential form of an equation. And you can always convert back and forth between them as long as you make sure to match up the various pieces of the equations that go together. So let's start with this. Being able to convert back and forth between the logarithmic form of an equation and the exponential form is an essential tool that you will need in order to work with logarithms efficiently. So let's do an example of converting from exponential to logarithmic. And vice versa. So I'll write down again what the definition. we've got that logarithm with base b of x equals y if and only if b to the y equals x. Now, some things that you can look at in order to help yourself out when converting here. Both the logarithmic function and the exponential function have numbers in them that we refer to as their base, and we use the same word because they are in fact the same thing. The base of the exponential function, exponential equation is the same as the base of the corresponding logarithmic equation. So that's the first part to match up. And then the most useful other place to look is here. And what I like to do here is to remember the following principle, that the output of a logarithm is an exponent. In an exponential function, the input to the function is the exponent. That's why it's called an exponential function. The logarithm function is the inverse of an exponential function, which means that the output of the logarithmic function is the input to the exponential function, namely the exponent. So the output of the logarithm is an exponent. And so the exponent that appears in the exponential form of the equation becomes the output of the logarithm, whereas the output of the exponential function becomes the input to the logarithm. So let's do a few examples. We know that 5 squared is equal to 25. This is an exponential equation. It involves a base, 5, an exponent, 2, and then the number on the other side, which is 25. So let's convert that into a logarithmic equation and see how we would write this down in its logarithmic form. So we'd go log, and now the base of the logarithm is going to be the same as the base of the exponential equation, namely 5. 5 is the number that's being raised to a power over on the left-hand side, and therefore it becomes the base of the logarithm in the logarithmic equation. Next, we say that the output of the logarithm is an exponent. The exponent of this exponential equation is 2, and therefore we get an output of 2 to this logarithm. Finally, the remaining piece is the 25. It's the output to the exponential function, but it's the input to the logarithmic function. So the exponential equation 5 squared equals 25 has the equivalent logarithmic form of logarithm base 5, or often just abbreviated log base 5, of 25 equals 2. When you plug the number 25 into the function log base 5, the output is 2. Because when you plug the number 2 in to the exponential equation, 5 raised to the exponent, you get 25. All right, let's see a few more. Let's see, if we take 1/4 to the third, that equals 1/64. That tells us that the logarithm with base 1/4, the base of the logarithm is the same as the base of the exponential. The output of the logarithm is an exponent. The exponent here is 3. And the input to the logarithm is 1/64. And let's look at one more. We know that 7 to the 0th is equal to 1. And that means that the logarithm with base 7 of 1 equals 0. Now, we're going to come back to this, but notice that there was nothing special about this situation. Nothing special about 7. If we plugged in any other number here, if we plugged in 2, if we plugged in 6, if we plugged in 1/8, any of those and raised it to the 0th, we would get 1 out of it. And in fact, this tells us that any of our logarithm functions, when you plug 1 into them, you get 0. So in fact, this tells us a point that is on the graph of every logarithm function, which we will look at when we go to graph these things. And it tells us that the point 1, 0 is on the graph of all logarithmic functions y equals log base b of x. This actually shouldn't be surprising because the point 0, 1 is on the graph of every exponential function. Now, we can use this conversion between exponential and logarithmic forms in order to evaluate the logarithm function for certain convenient numbers. So let's suppose that the question simply asked, what is log base 2 of 8? Well, we can solve this by setting up an equation where where we set a new variable y equal to this expression that we want. What we could do is we could let y equal log base 2 of 8. Now this is a logarithmic equation. We have a logarithm with some input gives us some output. Now in this case, one of the outputs is a variable, but that doesn't matter. We can still do the conversion. So if we convert this logarithmic equation into an exponential equation, we get 2 is the base of the logarithm, and so it's going to be the base of the exponential. The output to the logarithm, which is y, is the same as the exponent in the exponential equation. And then finally, the input to the logarithm is the output to the exponential equation. So we have that if y is log base 2 of 8, this quantity we're trying to figure out, then that's the same as saying that 2 to the y equals 8. Those are completely equivalent statements. And so now the question is, well, okay, 2 raised to what number is 8? In this case, we can work this out fairly easily. We may already know the answer. One strategy we can use here that helps is we can try to express the right-hand side in terms of the base on the left-hand side. And in this case, if we want to express 8 as some power of 2, we know that 8 is 2 to the third. So this tells us that 2 to the y is equal to 2 to the third. However, the exponential function is a one-to-one function, as we mentioned, which means that if the outputs are the same, then the inputs have to be the same. So if 2 to the y equals 2 cubed, then that means that y has to equal 3. So that tells us that log base 2 of 8 is equal to 3. Let's do another one that requires a little bit more work. So let's ask, what is log base 1/9 of 27? Let's do the same strategy. We're going to let y be log base 1/9 of 27, and doing that allows us to convert this logarithmic equation into an exponential equation. This becomes 1/9 raised to the y equals 27. That's the exponential form of the logarithmic equation on the left. Now we want to find what value of y makes this true. Now here, it's not quite as easy because we aren't familiar with a way of expressing 27 as a power of 1/9, like we would want to here. What we can do instead is try expressing both sides as a power of some other number. Not as a power of 1/9, not as a power of 27th, but find some way of relating the two. And in this case, the number 3 seems like a useful thing to do here. If we can express the left and the right-hand side in terms of the base 3, that'll allow us to compare their exponents and figure out what y should be. So going through this in a couple steps, if I've got 1 over 9, I could write that as 1 over 3 squared. And 27 I could write as 3 cubed. All right, getting there a bit. On the left, 1 over 3 squared I could rewrite as 3 to the negative 2. And then finally, on the left, I've got 3 raised to the negative 2 raised to the y. That gives 3 to the negative 2y, which is 3 cubed. And now we're ready to use the fact that the exponential functions are 1-to-1. So we know, based on what we've set up, that 3 raised to the negative 2y is equal to 3 cubed. The only way that happens is if negative 2y is equal to 3, is if the two exponents are equal to each other. And now that we have this equation, solving for y is just a matter of dividing both sides by negative 2, and we get that y is equal to negative 3/2. So our conclusion, therefore, is that log base 1/9 of 27 equals negative 3/2. Now, going through this process of converting to the exponential form and solving the resulting equation is typically what we have to do if we are going to evaluate logarithms by hand. However, there is a good intuition as to what the logarithm means that can sometimes simplify the process of evaluating the logarithm, but even when you do have to go through this process, it gives you some insight into what the logarithm actually is. So the intuition is the following. Log base b of x is the power you have to raise b to in order to get x. Now, this is really just a restatement in words of the definition of the logarithm, but it's a useful way of thinking about it. So, for instance, if I ask for log base 4 of 16, what I'm doing is what the logarithm is doing is it's asking, what do I have to raise 4 to in order to get 16? And sometimes we can do this. By hand pretty easily. We know that 4 to the first is 4, but 4 squared is 4 times 4, which is 16. So that means that 4 raised to the second power is 16, and that's the same as saying that the log base 4 of 16 is 2, because 2 is the number that you have to raise 4 to in order to get 16. Similarly, if I asked for log base 7 of 1/7, I'd be asking, right, well, 7 raised to what power is 1/7? And we know that raising numbers to the negative first power gives their reciprocal, so that's just going to be -1. Or if I asked, well, what's log base 10 of 1,000,000? That'd be asking, all right, well, 10 raised to what power is equal to 1,000,000? And we know that 10, because we use a base 10 numbering system, is very convenient when you take its powers, and whatever power you raise 10 to, that just tells you how many zeros you get in the result. So 10 to the first is 10, 10 squared is 100, 2 zeros, 10 cubed is 1,000, 3 zeros, and so forth and so on. So that means that 10 to the sixth is 1 million, which means that logarithm with base 10 of a million equals 6. Incidentally, this gives insight into something that we'll see in more detail when we get to the graph. The logarithm function grows very, very slowly. If you take a typical polynomial function that we've worked with and you plug a million into it, you're going to get an absolutely huge number. Even if you plugged a million into something like a square root function, you still get 1,000 out of it. There aren't a whole lot of functions that we're familiar with where you could plug a million into it and just get 6 out. The logarithm function grows very, very slowly. And you can plug quite large numbers into logarithms and get pretty small results. So, next thing that we want to talk about is a couple of special logarithm functions. There are infinitely many logarithm functions, one for each valid base, any positive numbers that aren't 1. However, there are 2 of them that are most commonly encountered in practice and theory. And we're going to see in the next section that these 2 are sufficient for everything that we need to do. In fact, even one of them would be sufficient for anything we needed to do, but for practical reasons, we still use 2 of them. And the first one is this last logarithm that we've just mentioned, the logarithm base 10. So we have some special logarithm functions. So the logarithm base 10 is called the common logarithm. Called common because of its common use. It's used in many fields. Part of the reason for that is that it's easy to evaluate, as we just saw, at least if you're plugging in powers of 10. And in fact, it's common enough that we have special notation for it. And the notation is simply dropping the base. So the log function by itself, with no base specified, is, by convention, logarithm base 10. So if you look at the expression log of 1,000 with no specified base below, then that is, by definition, logarithm base 10 of 1,000, which is 3, as we just saw last time. So this is called the common logarithm. It's one that you'll encounter quite a lot. Most calculators that you will see have the common logarithm as a button on it. And in addition to behaving well with numbers that are powers of 10, we can also see that it gives us some insight into other numbers when we plug it in, particularly as they relate to how they are expressed in our base 10 number system. So I'm going to pull up a calculator and let's evaluate the common logarithm of a few numbers. Let's look at the common logarithm of 732, the common logarithm of 64,321, the common logarithm of 7, and the common logarithm of 0.00036. And let's see if we can see a pattern here that allows us to conclude anything about it. All right, so pulling on my calculator. This is the same calculator I used before from Desmos. Now, you may have to go into one of your you may have to look for your function. In this case, we can see we've got logarithm right here. And we can start off, let's just plug in logarithm of 1,000, and we can see that, in fact, we do have 3 out of that, as we established before. And as I keep adding zeros, the value of the logarithm keeps going up by 1. So every time you multiply the input to your to the logarithm base 10 function by 10, the output goes up by 1, which is a pattern that also applies to all the other logarithms. All right, so let's get rid of all those, and let's a logarithm of 732 is 2.8645, etc., etc. And this is really all there is to it if you need to evaluate a logarithm, and an approximation will do, which is usually the case. Logarithm of 64321 is 4.80835, etc., etc. Logarithm of 7 gives 0.85409, etc., etc. And then a logarithm of 0.00036 gives negative 3.4436, etc., etc. So, a few things to point out here. First of all, you notice that we can get negative numbers out of the logarithm. In fact, this will happen whenever the input to the logarithm is less than 1. And that applies to any base larger than 1. We'll see this in a second when we go to construct the graphs. Negative numbers are possible to get out of the logarithm. Furthermore, we can see here that we've got the logarithm of 7 is less than 1, and that's because 7 is less than 10. The common logarithm is an increasing function, and if you plug in a number that's less than the base of your logarithm, then you'll get a number that's less than 1. But those are all things that are common to many of the logarithms that we look at. The thing that's nice about the logarithm itself is the following. Take a look at the values that we get out of here and compare them to the number of the number of digits in the number we're plugging into the logarithm. So in this case, we have a 3-digit number, discounting any decimal places, which we didn't have here, but wouldn't have changed things much. Let me go ahead and show if we had plugged in 732.5689 blah. That would only have changed the output a tiny bit. And you'll see that the number that we got out of that logarithm is between 2 and 3. The next one we looked at had 5 digits. It was a 5-digit number, and the output is between 4 and 5. Next, we've got a 1-digit number that's between 0 and 1, the output when you plug it into the common logarithm. And then the next, we have a digit that is less than 1, quite a bit less than 1, but you can see that we've got quite a few digits here. And in fact, if we consider how we would convert this number to scientific notation, moving the decimal place 4 places beyond the first digit beyond. So we've got 4 places to the first non-zero number, and our output of this function is between -3 and -4. So in fact, the output to the logarithm tells you how many digits were in the number that you plugged in. One of the places where this is surprisingly relevant often is in computer science. A lot of times you're working with numbers and you're having to program your computer to display certain outputs, but you don't know ahead of time what sort of outputs you're going to get. You've got some big program, it's going to come out with a number, but you don't know ahead of time whether that number is going to have 4 or 5 or 6 or 7 digits, and you want to format it. You want to format your output correctly. Well, one way that you can do this is with the common logarithm. If you use the common logarithm and put a number into it, that can tell you how many digits that number has. And so let me write down the conclusion there. Let me just handle it for numbers that are greater than 1. So for x greater than or equal to 1, the number of digits required to express x as in decimal notation, ignoring the fractional part, is approximately the roundup of the common logarithm of x. And that is, I should say, this is unless x is itself a power of 10. More precisely, we can do the following, and sorry, let me give the slightly more complicated but completely correct one that doesn't require the special case. It's actually the round down of logarithm base x plus 1. So for instance, we had that the logarithm, the common logarithm of 732 was 2.86, etc. And so if we take the round down of 2.86, etc., plus 1, the round down of 2.86 is 2, and adding 1 gives you 3, which is in fact the number of digits in what you started with. So you can always tell the number of, or you can use the common logarithm to tell the number of digits required to express that number in decimal notation. If you use other logarithms, then you get the same information for expressing that number in those bases. So for instance, if you use log base 2 in this same formula, you'd get the number of places required to express it in binary. If you use log base 16, they'd give you the number of digits in hexadecimal, and so forth and so on. So that's the common logarithm. It shows up often in many contexts, including scientific, engineering ones. The Richter scale for measuring the power of, or for describing the power of earthquakes is described using a logarithm with base 10. However, in mathematics and some other disciplines, log base 10 is not the most used logarithm. And part of that is because log base 10 is useful mostly because we happen to operate on a base 10 system. However, there's nothing mathematically special about the number 10 to make it useful as a base for a numbering system or as the base for a logarithm. In fact, if you ever wonder why it is that we use a base 10 number system as opposed to any other base, well, it's very easy to explain why. This is why. Human beings have usually 10 fingers on their hands, and we usually count using our fingers, and so having things being measured in units of 10 is intuitive and familiar, but there's no mathematical reason for doing it. If we were ever to encounter an intelligent alien species, we shouldn't expect them to use a base 10 system, unless they also happen to have appendages that are useful for counting and they also happen to have 10 of them, usually. There's nothing special about 10. However, there are some numbers that are important mathematically, intrinsically, and not just because of the way that we've chosen to write down our numbers. One of them is the number that we looked at last time, and it's Euler's number. Euler's number E, recall, is a number that's 2.71828, etc., etc. It's this number between 2 and 3, and it came up when we were looking at compound interest and what happens when you compound things continuously, every instant compounding interest on the interest earned at all previous instants. And this number E is important for a variety of reasons. And it's also very useful when we look at the logarithm with base E. Logarithm base E is called the natural logarithm and is usually denoted ln. If we write down something like ln of x, that really means log base E of x. Now, because E is not a whole number or even a rational number, this is usually not an expression that we can work out by hand for most values of x. But as I said, it does turn out to be extremely useful in many theoretical and practical applications. Now, a note on this notation. Why is it ln when the name is natural logarithm? Well, that's because it comes from the French. And in French, the adjectives often go after the nouns, and so the French happened to be fairly dominant at the time in mathematics at the time when some of this notation was being established, and so the natural logarithm is called ln because of the French Logarithme naturel. But it means the natural logarithm. There's not going to be a huge amount that we do specifically with the natural logarithm. It is more important when you get to places like calculus, and in those places it has some very important properties. For instance, if we look at the graph of the function 1 over x, and let's say we draw a line up here at an x value of 1, and then we stop at some point, let me call it a over here. And we draw a line up there as well. And we look at this region that lies sort of under the curve of y equals 1 over x and sits between the x value of 1 and the x value of a. Well, it turns out that the area of this region is exactly the natural logarithm of a. So that's one reason why we might consider it, honestly natural to use the logarithm here. Trying to come up with a similar sort of description for the common logarithm requires much more complicated functions than simply 1 over x. So the natural logarithm function is the other one that you will commonly encounter. Now, while we can't almost ever do it, calculate the natural logarithm by hand, we can in the calculator. Most calculators include not one, but 2 logarithm functions. And you can see my calculator over here has both. Just to the left of the log button for logarithm, there's the ln function for natural logarithm. So if I want to find the natural logarithm of 17, I can do that by going over to my calculator, saying natural logarithm of 17, and get 2.8332, etc. And we could do this with any number that we want. Now, an additional point that doesn't have to do specifically with the natural logarithm, but this is a good place to explain it. One of the things this implies, that's sometimes a helpful thing to note, this implies that 17 is between e squared and e cubed. Because the output to the logarithm is 2 point something, the output to the logarithm is some number between 2 and 3. That means that 17 itself is between e squared and e cubed. And the same thing does in fact hold for any logarithm. If I say that the common logarithm of 26, I know that this is going to be, I know that 26, is between 10 to the first and 10 squared, that is 10 and 100. So that means log base 26 is between 1 and 2. Because 26 itself is between 10 to the first and 10 to the second. So that's one of the relationships that you can see between the logarithm and the exponentials. So now finally, let's go ahead and explore that relationship strongly by graphing. Let's see what the graph of the exponential function, the logarithmic functions look like. We're going to use the exponential functions to do so. So let's look at graphs of logarithmic functions. So to do this, we're going to use strongly the fact that the logarithm functions are the inverses of the exponential functions. So let's consider some of the properties of the graph of y equals b to the x, the exponential function, and see what that means about the graph of log base b of x, the logarithm function. So we know that the exponential function y equals b to the x has a domain of all real numbers. It has a range of all positive numbers. It includes the points 0, 1, and 1, comma b, and it has a horizontal asymptote at y equals 0. These are the 4 points that I want to translate into information about the logarithm before we even plot points. So we have that the logarithm's domain is the same as the range of the exponential. So the domain of the logarithm is the same as the range of the exponential from 0 to infinity. The logarithm is only defined for positive numbers. The range, however, the range of the logarithm is the same as the domain of the exponential, which is negative infinity to infinity. And then remember that when we have a point on the graph of a function, then we can find a point on the graph of its inverse by simply switching the roles of the input and the output, the x-coordinate and the y-coordinate. So because the graph y equals b to the x includes 0, 1, the graph of the logarithm will include the point 1, 0. And because the exponential has 1 comma b, the logarithm will have the point b comma 1. And then finally, a horizontal asymptote at y equals 0 becomes a vertical asymptote at x equals 0. So let's graph a specific logarithmic function and see how it goes. So let's look at let's suppose we want to graph the logarithmic function y equals log base 2 of x. Well, I actually want to also graph y equals 2 to the x at the same time. If we graph the exponential function, that can honestly help us quite a bit with graphing the logarithm. All right, so let's see how this goes. So let me start off by graphing y equals 2 to the x. So let me just plot some points. We know that the point 0 comma 1 is going to be on the graph of 2 to the x, and the point 1 comma 2 is on the graph of 2 to the x. That we always know. And we have a few more that we worked out previously. We know that the point -1 comma 1/2 is on the graph of 2 to the x. If you plug in -1 there, we get 1/2 out of it. If we plug in 2, we'll get the 0.4 out of it. So let me take these points here and say, all right, well, what does that mean for the logarithm? That means that the logarithm includes the points 1 comma 0 and 2 comma 1, as we mentioned before, but it also means it includes the point 1/2 comma -1 and the point 4 comma 2. All the points on the logarithm, on the graph of the logarithm, are simply the reverse of points in the exponential. So I'm going to graph both of these. I'm going to graph the exponential in blue and the logarithm in red. So in blue, we've got the points 0 comma 1, 1 comma 2, -1 comma 1/2, and 2 comma 4. And we have that horizontal asymptote at y equals 0. And the graph goes up like that, increasing very, very quickly. On the other hand, the graph y equals the log base 2 of x includes the points 0 comma 1. I'm sorry, 1 comma 0, 2 comma 1, 1/2 comma -1, and 4 comma 2. And it's going to have a vertical asymptote at x equals 0. That is the y-axis. And so that's what the graph of y equals log base 2 of x is going to look like. One thing you can notice is that these two graphs are symmetric in the sense that they are reflections of one another across the line y equals x. We mentioned this back when we talked about inverse functions in general, and of course it holds true here, that the graph of a function and its inverse are symmetrical when reflected across this line y equals x that goes through the origin and has a slope of 1. This is the graph of y equals log base 2 of x, and graphing out the exponential function first and then just switching those points around to get the logarithm is often the easier way to do things. Because while the logarithm carries exactly the same information as the exponential function is often more intuitively easy to work with. All right, let's do another example where we look at a base that's less than 1. So let's graph log base 1/3 of x, or y equals log base 1/3 of x. Again, I'm going to start by figuring out what the graph of y equals 1/3 to the x looks like with a few points, and then use that to figure out the points of y equals log base 1/3 of x. So if we have 1/3 raised to the x, we of course always have the points 0, 1 and 1, the base 1, 1/3. We also have the point -1, 3, so -1 to the third, or I'm sorry, 1/3 to the -1, other way around, sorry. 1/3 to the -1 is 3. And then let's see, we could say we've got 2, 1/3 squared is 1/9. So we've got these 4 points, which are going to help us to see what the graph of 1/3 to the x looks like. And then for log base 1/3 of x, the points on this graph are all reverses of the points on the exponential. So it includes the points 1, 0, 1/3, 1, 3, -1, and 1/9, 2. So let's see about graphing this out. Let's see. I'm just trying to estimate how much room I'm going to need. Get all these things filled up. Let me put my calculator away. Let me actually do that up here. All right, so let's see. I want to count by 3s this time because we got those 1/3s running around. All right, once again, we'll graph the exponential in blue. We have the points 0, 1, 1, 1/3, -1, 3. There's that point way up there. And 2, 1/9. So that's going to be very close to the x-axis. And so the graph of the exponential is going to look like this with the horizontal asymptote at y equals 0. And going up like this. Whereas the logarithm contains the points 0, 1, 1/3, 1, 3, -1, and 1/9, 2. The inverse has these up here. Remember, it has a horizontal asymptote at x equals 0. Goes down through the point 0, 1, through this point over here, and looks like this. So there's our graph of y equals log base 1/3 of x. And these are the two basic shapes that the logarithm can have. It will either be increasing or decreasing with exactly the same criteria as for the exponentials. It'll be increasing if the base is greater than 1, decreasing if the base is less than 1. It always passes through a couple of special points. It's always going to pass through the point 1, 0, and it will always pass through the point b, 1, where b is the base. And then it will always have this vertical asymptote at x equals 0. Having graphed out the functions, this keeping them in mind can help you to remember how the logarithm behaves, that its domain is always just positive numbers, that its range is always all real numbers, and the various other properties that we can tell from the graph. Furthermore, transformations of these functions, such as shifting up and down and left and right, stretching and compressing vertically and horizontally, work just as well on the logarithm functions as on any others. So you can do that. I recommend that when you have a problem like that, you start off by sketching the basic logarithm function that you're working with, and make note of the asymptotes and probably 3 points on the graph, like we've done here, and then trace what happens to those points as you go through the transformations.